Hi, welcome to the lab. So in the last videos, we built a very small arena allocator, and also we worked on parsing regular expressions. I want to put them into use today. So we are currently building a scanner generator library. So for example, I would like to specify a scanner, or let's say sorry, gotta stop my music, which is running in the background. I want to specify a scanner by writing its tokens in a list, similar like this. So first of all, we're building a library, which is then later, for example, can later be used to create an actual scanner generator tool, such as, how is it called? Flex, I think. Yeah, Flex is, I think, is. So I'm always mixing up Flex and Bison, but I think the Bison, so it doesn't really matter. So basically we're defining tokens like this. And so tokens which are defined by a single string, such as symbols and keywords. We support them already, but to support tokens, which, for example, for literals, where you give a pattern and all of the character combinations described by this pattern. Yeah, so basically I should have thought of a sentence before I began talking. So basically some tokens are unique and given by a single string, and those we already support, but we don't really support tokens that that could have potentially multiple values, such as literals or white space. And there you use regular expressions, where you could, for example, also use other meta languages for describing patterns, but I chose to use regular expressions. And so basically we're currently working on supporting those. For that, our program has to understand them, and so I built a small parser, which is also already opened right side here. Yeah, so and also we did some unit testing, and our regular expressions isn't really sophisticated, but it supports basically single characters, alternatives, concatenation by juxtaposition, alternatives using like the pipe operator, the bar, but also the typical repetition, the empty repetition, the cleany operator, or calling it positive cleany, so the repetition where you need at least one element, or for example the optional character, and also of course character classes such as A to Z, lowercase A to Z, and yeah, so also we should also be able to combine those atoms with the other operators, which I haven't tested yet, but I think, yeah, I don't know where to start, so I would like to do something else. I don't want to work on tests today. So this is basically the state of the project. And yeah, so basically now let's clean our window. Where can I close everything? Sure, close everything. So it's, oh! What was that? Okay. So basically, I would like to work on this example. And do so, I am thinking to resurrect my old main. And I want to keep running my tests. So let's just try this out. What does this code actually do? I think it runs my tests and then prints the automaton, which we already parsed. So we currently, I just print all of the automatons of the tokens that I'm defining here. So for example, this one should be the first automaton of the first token, which I'm just calling test here. And this is the automaton which always accepts. And then we have an automaton which accepts a single, expects a single character. So let's talk about what this actually means. So we start in state 0. This is the start state is denoted by the asterisks. And then if you are in state 0, when you see a plus, you can change your state to state 1. And states which are in parentheses, this means this is an accepting state. So this is a transition from state 0 to state 1, and 1 is an accepting state. So similarly, this is the automaton which which accepts the input string for each. So we start in state 0, then we transition in the next state, and you might see this is a chain, so a chain of state transitions where each successive state, each transition accepts one character, and if you, I think you see what I mean here. So if you follow the chain of transitions, you see that you can, this automaton accepts the keyword for each and accepts in its 7th state. So but now let's also try to do this. Until now, I'm just accepting literal tokens. Today, we want to start working on turning regular expressions or our parsed representation of regular expressions into automatons. I should have said this a lot earlier, but this is what we are going to work on today. So, and of course, currently we get an assertion since somewhere we have a case which is not really implemented. I think here. So in this case, we should build an automaton. So, but first of all, I would like to do something else. So let's see. I would like to, where do I build the automaton? Here I do this. So basically, we have a automaton class, which is a builder for an automaton, basically, and non-deterministic finite automaton. And currently we use malloc, I think, to allocate its kernel state. But since we introduced so I'm just newing its internal nodes, and we are leaking it. So maybe as a first change, I don't want this. So since we already introduced an arena allocator, we can just reuse this and allocate everything to one single arena. So let's create an instance, and let's just pass it into our automaton class. So of course we allocate the list, the metadata structure, the list data structure, currently not living inside of the arena, but I won't care. Don't care right now. So let's just remember the instance arena. So finally. So I think now I can just send the constructor. Oh, of course I want to capture the reference. So constructor, and mark this explicit and Now we just gotta implement this. So of course now we're just going to remember this. And now we don't need to delete anything, I think. Just clear the list, since the memory gets deleted later. So this just, so I want, so let's see. We have new calls those places. So in this, instead of this, we're now going to use our method called construct, which we're just giving a state, the type, then the types arguments. So does this work? No. Why not? Oh, this is the ID, I think. So I think I should create a constructor for my state object. So and now for the transition, it accepts the states, or the origin and the target state. Okay. Origin, target. Forgot explicit here. So then, of course, we are allocating an arc. Sure. Okay. Oh, and of course, so now we're allocating everything, every node into our arena, so we don't have to delete anything. So I think we can just clear the list and do nothing with its elements. So instead of iterating through the lists, we're just clearing them. So this should be fine. Oops. I don't know. I think this should be a copy-paste error from the past. So now so let's just rerun our code and see if our change worked. But of course, let's if this out again, since, well, we have an assertion which crashes our program. Oh, but this looks fine. So now we don't using malloc very often anymore. So let's just commit what we got. So, and now what we're basically going to do, we're writing a function. So let's see what we do here. So what should I? I'm passing single NFA here, but this method will now pass regular expressions. So I need the arena instance. So let's just start. So basically, what do we have here? Okay, we're going to work on this case. So let's now, how do I get the pattern? I think token.pattern. And we know that our type is a regular expression. So sure, this should work. So then I should just be able to include our regex parser, and I'm going to make an instance of it. We have a parser, and it requires an instance of our arena, which we don't have in this method. So we're just passing it in. Arena, one arena, rule them all. Passing it down. So now we have a parser, then we can initialize it with a input. Our input is token.pattern. This should never fail, this operation. But now if we call parser.parse, this operation can fail. So So if we have an error, I think we're just going to this method. So no error propagation. Well, so let's work on this a little bit later. So in this case, I'm just going to print the error message. And return false. And let's remember that we got to do some error propagation later to error. Yeah, sure. So, and then let's deal with the happy case for now. So in this case, we didn't return, then we have a regex free. So either regex right. So in this case, we should have a regular expression. So let's just see what happens. Let's see if we actually reach to this point. And we do. We got called by the pattern. So basically the pattern 0 to 9 plus did pass correctly. Let's see if our tree is plausible. We don't see our tree. This is a valid pointer. No. So let's see if we can just print it. I think we didn't import our tree, so compiler has no idea. Now I see what the problem was. So now I should now I should be able to print it, and also the compiler should know how to show some information. So we have basically we have the correct node here. So let's see. Let's remove this. So basically what we do now we have a regex and we need to turn this into an automaton. This will be fun, I think. So do this. So how are we going to do this? So I think we need to draw some images. So I have got to draw some images to know how we actually would like to achieve this. So let's start simple. I think I need a function for that which returns states. Oh. So let's think. So basically, now I have a way to turn regular expressions into trees. For example, let's start simple. The regular expression a, for example, corresponds to a very simple tree, which just denotes, I think. And to build so let's just say this is the pattern. Let's just call it Rx for regex. This one is the tree. Well, so I'm writing with the mouse. It is really, really, really beautiful. Oh, tree. I can't mouse today. Oh, tree. Oh, fine, it's fine. Here we get the NFA, the automaton, Nondeterministic Finite Automaton. So, and a simple A, for example, turns into a, I don't know how I want to model this, I think. Let's do explicit states here. So what I'm thinking of doing is for an atom, we're just going to construct a very simple automaton, which consists of a start state and an end state. We will do this for every case, I think. It would be really easy to merge then and combine different automatons to a bigger one. So in this simple case, we're just going to create a state, a start state, end state. I'm just inventing some names. This one accepting, so I'm using the notation. I'm circling in states. States with an ingoing edge without a label are the start states, and states with an underline are accepting states. Well, basically this arc is labeled with an A, so to transition from state S to S prime, you've got to see an A. So the A is not really visible. So this is our simplest case. So I somehow just learned a shortcut for this program. How can I somehow draw a straight line with a shortcut? Well, doesn't matter. So then, if we have a simple regular expression, so this is the trivial case. Let's consider. So I think. So I'm thinking the classes and alternatives. For example, A, B, or A or B. So basically an alternative in class is basically just a big alternative. So I'm handling them similarly. So that they are given by a different tree, but this doesn't really matter in our case right now. So so I see a problem here with my internal representation, but it doesn't really matter. So those have, so basically my trees, so I differentiate those trees basically. My atom representation, my atom nodes are implicit alternatives, but let's consider this case. So we have so we get a tree similar like this one. So this one is the bar operator, and we have the left-hand side and the right-hand side under those. And in this example, those letters, so of course this can't, this don't has to be a single letter. This can be an arbitrary complex regular expression, but in this case, A and B must be letters, so single digit characters. So, and in this case, I think we're just going to create a simple automaton. I'm using the same letters here. So to detect an A, we have the similar structure as here above. Well, this is getting ugly. So I think I'm abstracting our structure really fast. So we have a automaton which detects a single A, and we have an automaton which accepts a B. And it is accepting. So, and to combine them in an alternative, I think we have to do one of the following things. So we have this tree and this tree. Then we have to create an synthetic node, which will be the new start state. And we are connecting old start states of the underlying automatons. And this transition will be an epsilon transition. So you don't have to consume a character to transition from this state into this state. And likewise, you have to remove the flag that this state is the accepting state and have to synthesize a new end state. So basically, those states stay, but they are not end states anymore. Similarly, we can then introduce epsilon transitions from the old start states into the new synthetic one. So, and I think can do this for almost every regular expression. So this for the alternative, the concatenation, which is just, and now I'm using capital letters, which are not, I mean by that, not single characters, but arbitrary automatons. So then, and let's use a different notation. So this is a black box containing a regular expression, which an arbitrary complex automaton, which has one start state and let's say one accepting end state. So this internal automaton, and well, we have such a thing for A and B. So, and I could have done this here as well. So this one is basically the if I would have labeled this one A, uppercase A, I could collapse this to the combined automaton. But this, I think my cat redecorates my room. Hey! Don't know what she's doing. So for a concatenation, of course, I have two automatons, which basically one accepts this regular expression and this accepts this. So this accepts this one, and I think I can just combine them into a new combined regular expression, and then I can abstract away over the internals. And if I do this like doing here, so I always have a start state and an end state. I can always inductively create the resulting automaton. And I think for simplicity, so for example, I don't have to synthesize a new end state if during combination I could have a list of accepting end states. But I think for simplicity, I'm always going to synthesize a new start state and a new end state where necessary, of course. Maybe if I already have only one, then I don't need to synthesize one. But I'm thinking I'm keeping this structure. So I'm always having a single start state and a single end state for each step during combining automatons. So, and let's consider a similar case. If I have, for example, the regular expression A star, then I have a regular expression, an automaton which detects A. So I think I then need to synthesize a new state. And this transition is an epsilon transition. And then I'm synthesizing a new end state. This one is an epsilon transition. But also we introduce a back loop, which is an epsilon transition. But if we are in the start state, we can also skip everything, which is also an epsilon transition. So I think we can do it like this. So now I can, if this is the start state, so in this case, breaking my notation. So if I'm starting in this state, I can see nothing because I can skip the whole thing. So I think I can skip so basically I think I can spare one state here. So if this is my end state, let's just see if we can compress this a little bit. I then can just basically create an edge like this, but it doesn't really matter. So I can see nothing. I can see the whole thing once. And I could also potentially see the whole thing multiple times since we have the looping edge here. So, and of course, we synthesize a new edge. This one won't be accepting anymore. This one will for the complete automaton. So, and I think we can do this similarly for plus, except we won't have the back edge. This first edge, okay, which skips the whole thing. So basically, we just have an automaton which detects A. We have its start state here, we have its end state here, and we're just creating a back edge here, and this should be a plus. Forgetting the arrow. And I think similarly we can do the alternative. Also, no, sorry, the optional, which is just a combination of this and this. So this is just a combination of this and this. I already see that. So I'm thinking if I just want to drop, I think I can just drop the plus, because, so let's just finish my thought. Of course, a star is either I see the operation, the old automaton, or I can just skip everything. Well, I can skip everything using an epsilon transition. So this should be this whole resulting operation. So basically, what I was thinking of, A plus is just A star. Well, I think I can actually simplify my tree. Well, I could also express this a little differently. I could also drop the cleaning operator, since the cleaning operator is just a option. Oh no, sorry, it's not really. Oh, not really the case. But I could drop this case. Maybe I'm doing this. Well, simplify. So I have to consider one less case. But I think it doesn't really matter. So since it will be pretty easy. So what did we learn? We need a function which gives us a tree. We get it, and we get a function from a tree to something which returns the start state and end state. And that should be it. So let's see. Let's see. So I think it will be an inductive process, so a recursive function. So, and I think it won't fail. It can't fail, since we already passed our regular expression. So this operation, I think it should not be able to fail, but let's see. So, and we return something which contains a start state and an end state. So let's say we return a struct which we are calling in the intermediate NFA. Let's call it, give it a stupid name. So let's see, what does our state? We have a start state, and an end state. And this, I think this should be it. So, and we initialize it by null pointer. Whoops. So now we introduce a new function which returns a intermediate NFA, and we call this one and I pass it a regular expression tree. Like this. So now we have to switch over all cases. So let's remind ourselves what trees we actually have here. So basically I can just use the IDE's features. So this case should be impossible. So let's just assert false and unreachable. So we just crash. In this case, I think I can return a dummy the dummy value, but of course this assert will crash, so I don't need to consider this case. So now we just gotta handle all the cases. So let's see. Let's deal with atoms first. So in case of an atom, so let's just cast our tree to an atom. So atom. So what does an atom have? It should have a character class, I think. A character set, not a character class. So out of a character set, I have to construct a big alternative. Now I don't need this. So since my edges, basically my edges are already alternatives, I don't need to build. Yeah, so I think it is really simple. So and of course I think I need to pass in my current automaton, since this is my builder basically. So regular expression and the automaton builder. So in this case, if we have an atom, I can just create a state. This one is the start state, and this one is the end state. Create state. So this one, start state, we configure it as the start state. The end state we configure as an accepting state. So I'm calling them accepting states here. And then we are going to introduce a transition. Create arc. So I just need to use the states first. So between our start and the end state, we have a arc, which we just assign the atom's character set. I think this should be it. So this is no epsilon transition, so everything should be fine. And then we can just, let's introduce, I just can turn start end, I think. Start end. So, and let's do a dummy implementation for all of those cases, so that I'm just going to, I'm just able to run this. Let's just say, oh, invalid. I'm also already handling this. Implement. So doesn't really matter what I say. Yeah. So this should be it. Create regex automaton. Okay, sure. So then I can just call this here. Create regex automaton. Regex. Sure. So does this work? Does it build? Does it work? So and sure, of course we reach this case. So let's use a simpler testing case for now. Let's simplify. We are just giving it a single character as a literal token. Okay. Should be the last case. So this one worked. This is perfect. And watch what happens if I give it a class. So for example, A to Z. So then we get automaton with all the possible cases as a potential label for its transitions. It works perfectly, our simple case. So then let's work on the, don't know where we should start, the alternative, I think. So let's just do it. So alternative. What did we say? So let's redraw this without the internal structure visible. So if we have a regular expression AB, where A and B are more complex regular expressions, we have an automaton which is called which detects A. This automaton has an ingoing, so an accepting state and an accepting state and starting state. And the same thing exists for B. Well, I don't know why my mouse does, I can't draw straight lines with my mouse. So, and then I think we're just inventing a new state, a new start state and a new end state, and let's just produce epsilon transitions for those. So, doesn't work. So, and then of course this won't be an accepting state anymore, and this one won't neither. Those are just epsilon transitions. Let's just do it this way. Hello cat. Do you want to play? You just ate. Meow meow. Okay, so let's start by casting our alternative. Of course, stays const. So, and the first thing we're going to do, we are going to use the same. So we do the following thing. We do the let's just call it left and right for A and B. So we're just calling the same method with alternative with its left and with its right component. And of course we have to pass in the automaton builder as well. So what's your problem now? Okay, but I can accept it as a regex. So left and right return a reference. So let's not dereference our data here. Oh, let's just keep it as a pointer. Since I think this will be a little bit cleaner. It will be more clean. Pointer. No dereference. So the formatter will stay the same. This one is fine as a reference. So I think we just need to fix our printing, since we here use. So I have to dereference those now, since our formatter works with references, not with pointers. So just going to dereference everything. So now it should still build. So join us, little cat. Come here. I don't think you can see her. She is here. But I can't turn my camera anymore. So she will stay here and help me debug. So now we have the left automaton and the right automaton, where left, of course, is here A and right I'm calling B, this image. So currently we're looking at this image part. So A is left and B is right. So then let's first of all introduce a new accepting. I think I can do this in almost all cases, but let's just do it. So we're just inventing two new states. New start state and end state, which we reconfigure as being start and accepting. So then I have to drop start and the end state status from left. So left.start not so with the start state of the left automaton is no start state anymore, and so let's and the wait and the end. Yeah. So the start state of the left side is now not the start state anymore, and similarly I have to drop the statuses from the right side, and then I can wire them up. So then I can connect start with left. Yeah. So now I just gotta wire them up. So automaton create arc. We're creating an arc between the start state and the left automaton. So the start state of the left automaton. And this arc, I think we don't really need to remember this. This arc will have an empty char set, but we will flag it as being an epsilon transition. Okay, so I'm thinking creating some helper function. So let's maybe do this later. So I'm rewriting this later, just going to write the code. So of course I can also, I don't need to remember the arc here if I'm doing this similarly doing it like this. So this is not really the most beautiful thing, but well, I'm going to rewrite it. So from start to left start with an epsilon transition, and similarly I can do this the right start, and then of course we need to also create some arcs between the end state of the left automaton with the new end state, and it will also be an epsilon transition, and we will repeat this for our right side. Then I'm just going to return the new synthetic start and end state. So I'm thinking this will be it. I think this is it. So alternatives should work now. So let's see. Let's actually see. Let's call this token test, since, well, previously it was called literal and it triggered my OCD. So let's see if this actually worked. So so this is really ugly. So char sets, the transitions are printed really ugly. So let's fix this. Our NFR, we have a print function somewhere. We have it here. And the args. Where are they printed? These are states, indentation, args. Where are you printed? Here. So basically we just have to print. So the char set is printed as an empty string if it is empty, but we have to, I see what we got to do. So if arg char set, when the char set is non-empty, we have to print the comma here. Oh, stop it. So of course we don't have a char set is empty or non-empty method. So let's just do boolean is empty. And also let's do non-empty. I'm just going to implement it like this. So now I just have to implement is empty. Let's do this. Put it here. So empty is empty. A character set is empty if nothing is set. So okay, let's just steal the loop. And let's see. So if E is set, if one of the characters is set, it can't be empty anymore, else it is empty. So not really efficient, but doesn't really matter for now. I think this should be it. So now I think our automaton will be printed a little bit more. Did it work? Yeah, so now we just get the word epsilon instead of comma epsilon. Okay, fine. Cool. So let's see. We have a start state. Let's just see what it actually created. So okay, let's draw what we have here. So let's see what we have here. So we have a start state, which I'm using the same labels as in the printout. And we have a transition from 0 to 2 and from 0 to 4. We have epsilon, those are epsilon transitions. So epsilon here and epsilon here. So we have a state 1, which is the accepting state. I think I'm just going to draw it at the end. It's accepting. And then we have from 2 a transition to 3 by seeing an A. So a transition from 2 to 3 when seeing an A. 3 is not accepting. Then we have a transition from 3 to 1 using epsilon when seeing epsilon. From 4 to 5. Well, 4 to 5 using B, and then from 5 to 1 with epsilon. So I'm just copying this printout and turning it into a visible, a graph representation, basically. This looks great. This is an alternative. You can either see A or B, and we have a lot of garbage states, but it doesn't really matter. We're going to eliminate epsilon transitions later. So in this step, just correctness is key in this first step. So now I think this we need to do a lot of those things. So let's just say the following. So I think I have to do a lot of those wiring things, a lot of those wiring epsilons. So let's just introduce a new method, which I'm just going to call the epsilon arc. And we pass in the automaton builder and two states. So let's call them A and B. And we're just going to create an arc from A to B. And we're just flagging them as an epsilon transition. Okay, now this method I'm calling here. Yeah. So this one we already got. Then I can just automaton, and I'm just going to do some refactoring here. So I think this reads a little bit nicer. So in this one, I think I can do them in every case. So every case will synthesize a new start and a new end state. And in the case of an atom, we're just creating an arc between them, returning those. So we will always return those, I think. Maybe we can always always return them. Then of course we got a break in every case. This should be fine. And of course we have to repeat those. So those steps. Let's just also create a helper for that. Basically, we give it a NFA and it just nukes it. Start and end configurations. Okay, let's do this. So drop config, for the lack of a better name, and we pass it in intermediate NFA, and it just does this. Then we can just do this for the left-hand side and for the right-hand side. It should be a little bit more clean now. Okay, sure. So I think alternatives work. Let's work on concatenation. So let's build a test case. Let's just pass A and followed by B. Just let's run it and see what happens. So I'm expecting, of course, that this assert fires. And it does. Sure. Now let's introduce a separate case. And I think we also have to, first of all, we have to cast our tree on concatenation. And we also have to create an automaton for the left-hand side and the right-hand side and drop their configurations. So if I give those a shorter name, so this one is just called regexp. I call it R. I spare the weird line break. Let's just call this expression. And this one also. Of course it is a token, but I think it is clear in in its context what type it actually is, and so the code flows a little bit more nice. Okay, sure. So now I have a left and a right, and I'm dropping the configuration. Now I just got to wire the states up. So I create an epsilon arc between the new start state and the left, the start state of the left automaton. Then I'm creating an arc. So let's draw this out for better visualization. So I have the I'm drawing them in the, so I have the left and the right automaton, which is here called left and right, and here L and R. Of course, it has an ingoing state and an outgoing state. And so I create a new start state for the whole thing, the new end state for the whole thing. So start is this one. Start. Of course, this one is left start. So I'm wiring those up using an epsilon transition. And then the end state, so left.end and right start. So this one, well, I don't know why this looks more like lightning instead of a straight line. My mouse stutters a little bit, so okay, like this. And then of course I got to wire the right end state of the right and the new end state up as well. Yeah, so in this case I could, for example, spare those two states if I'm just reusing those. But I think I'm just going to keep this, since it's a nice way to generalize the inductive concept. We can also always optimize it later. So let's run this, see what we get. So now the labels are, of course, not really perfect, but let's draw it next. So we have an automaton which starts at state 0. We have a transition from 0 to 2 to state 2. And this is an epsilon transition. And then we have a transition from 2 to 3 using, in this case, A. Well, this is not a beautiful A. Really ugly indeed. So I don't know what I'm doing here. I switched the tool. So A, and then from 3 to 4 using epsilon. And then from 4 to 5 using B. I think this makes sense, this automaton. And from 5, state 1, N1. So an N1 is accepting, denoted by the parentheses here. Epsilon. So I think that this should be it. So we have state, we can detect an A, B, only then we accept. I think this worked perfect. So concatenations, I think, are done. Let's start with a new document here. So let's do first. No, let's just keep the ordering. So then, oops, let's cast this to key. So of course we just now have only one automaton. So we have the, let's call it left right. Let's call it wrapped. Or underlying or something. So, and then we drop the config, drop config wrapped. Okay, sure. So now we get this automaton. We get an A, which is an arbitrary regular expression. It could be an arbitrary complex automaton, 2 states, and we drop their configuration. So this one is not flagged as a start state, and this one not flagged as an end state anymore. So, and we already syntheticized a start and new start state. Whoa, now a state, a new end state. So this one is the start state and this end state. Now we got to wire them up. So I open this to each other. This would be helpful. This, I think this will be a little bit better. So hide this. Okay. So then, of course, we have to create an arc between the start state and the old start state. So let's do this. From our start state, our synthetic start state to the old start state. So now we have this one, Epsilon Transition. And also we have the ability to skip it. So this is the accepting state. Oh, sure. So let's also wire this one up. So then we have basically the possibility where we don't see anything. So we wire the start state with the end state, with the new synthetic end state, of course using the Epsilon transition. Then we also got to introduce this transition, which is between the end state, the new end, and we need the loop back. So let's just invent a new transition from the end to the start state. And I think this should be it. So now we kept the original automaton completely alone, and we just expressed our construction using the old states. But is this fine? Be fine. But I could also use those. I don't know if this works. So what happens if I embed this into another regular expression? But should I just express this in terms of this? So I think I will do this a little bit different, just to be sure. Let's go back a few steps. So this transition should be fine. And let's let this one basically be a commit. So if you enter this state, you can't leave it, just to be sure that our when combining automatons, that our construction is hygienic. And then we introduce this one as the new back label. And we also introduce a transition which goes here from our start state. I mean, I could also express this in terms of completely this. Well, let's see if this causes a problem. Let's do it this way. See if it causes a problem. I think it should be fine. So how can I? So I don't know how to get back there, but let's keep it this way. Let's just try it. So let's see. If I, for example, say A star, how does our automaton look like? So A star, we have first of all a new start state. Sure. So start state is denoted by a asterisk in here. So I think I already said that, but just I'm looking at this. So then from state 0, we have two transitions, one to state 2 and one in state 1. So let's implement this. So from 0 to 1, 1 is accepting, and I see this because it is in parentheses here. State 2 by epsilon. So then state 1 has a back edge to 0, epsilon, and 2 reaches 3 when in A, so 2, 3, position A, and 3 using epsilon reaches state 1. So I think this should be fine. So let's just, for example, if I want to see an empty string, I start at 0, then I can transition into 1, fine. If I want to see 1A, one single A, starting 0, then I'm seeing epsilon, then NA, then I'm at 1. So then I accept. But if I see another 1, position back to 0, back to 2, see another 2. So I think the automaton is correct. Let's just working on all the missing automaton. So now let's clear our picture. So now we have a similar thing. We have A plus. We have an automaton which I'm calling wrapped here, which basically looks like this. And we would like to repeat this, but have to see at least one repetition. So we have to pass through this automaton once and have to repeat as often as we choose. So in this case, I think we always have to pass through our automaton and can accept. But then, of course, we can always go back. So like this. I think we can always go back to this. So, and of course, every transition is an epsilon. So let's do this. So we can sorry, my nose started to run really bad, so I lost concentration. So connect the new start state with the static start state. We connect the end state from our nested automaton with the synthetic end, and then we introduce a back edge from the end state to the start state. I think this should be it. So, and similarly, I think I'm reusing this picture. If we have an optional automaton, I'm just going to increase all the boilerplates. So this and this one. So like this. So we have the nested automaton, and we can, of course, we can see we have to pass through our nested automaton exactly once or no times. So I think we can just have to connect the edges like this. So then just we can take those and then from our start state to our end state unconditionally using. So I think this should be all our cases. So and then this should be inductively, and ignore the return value. In this case, since the construction is done implicitly and we don't need to we don't have to care about the automaton which we get back. Or do we? Do I have to remember it? Do I have to return it? No, since this automaton gets modified in place. So the construction configures the states and the transitions and does what it should do. I think this works now. So let's test it for example. Let's just uncomment the cases doing here. Let's just see what happens. Okay, no crash. Let's see what we get here. So we first of all, so this is a test basically. So let's just skip the simple cases. So and then we have our regex tokens. We have literal and white space. Let's see how they work. So this looks like a literal token. I think it works. Our white space token. So, but they have the same structure. They also all use positive cleaning. So let's do a more complex example. Let's introduce a test token Identifier. Did I spell that correctly? Yeah, of course. Identifier, perfect. So let's just define the regular expression for C identifier. So at least one character followed by optional so at least one character or an underscore followed by arbitrary amount of letters digits or underscores. So just run it. Check. Let's check the automaton. So this should be it. Let's try to draw it. Remove everything from here. Well, I should have just created a new document. So let's draw this automaton. Starting at the top. So we first of all have a state called 0 with a start state. Then we have a transition from 0 to 2 using epsilon. Sure, here you go. So from 2 to, which cases do we have here? 2 to 3 using, so these cases are, so those are all only letters and underscore. Letters, underscore, no digits here. Yeah, so from 2 to 3 using, so I'm using a shorthand notation here. A to Z, capital A to capital Z, and underscore. So, nope. No, now I'm satisfied, more or less. So, and from 4 you can reach, from 3 you can reach 4 by epsilon, and 4 has 2 transitions to 5 and 6, both by C epsilon, epsilon, well, and 5 you can reach 4 or a back edge by epsilon. 5 can also reach 1, which is accepting by epsilon. So 6. From 6 you can reach 7. Okay, sure. 6 you can reach 7. But this one is, so this has gotta be fun. So let's just use the text tool. Is there a text tool? There is. Perfect. Okay. A to Z, A to C, so every letter, ASCII character, of course, ASCII letter, and then digits followed by 0 plus 9. Hello? Hello? Okay, sure. It's a little bit small, but yeah, well, at least you can read it. I'll make this a little bigger. Well, I think it is perfectly fine for now. And of course, we are missing one transition from 7 back to 5 using epsilon. What? So I think I've selected the wrong layer. So like this. So this looks really ugly, but I think it should correct. So let's see. A C identifier is of course a character, which you always have to see, nothing to accept in the automaton up here. Then to reach state 3, you can either follow the chain of epsilons and accept, so you can see a single character, but you can also follow this path, the n letter which also contains digits. And of course, here then you can reach state 5, where you can either accept by using this transition, or you can loop again. So I think this automaton is correct. So I think this works basically. Really happy. So now I can create non-deterministic finite automatons out of my specifications. So each token creates a single regular expression currently. So a single automaton. And just for curiosity, let's see if we are done. How many blocks do we allocate actually? So let's peek into our arena. We have still one block. How? Well, we have allocated 9,000 bytes, so we are about halfway through our first block. So we did some allocations, but it should be fine. So still there are some calls to malloc using our lists. Maybe you can allocate from arena. This would be cool if you could pass in a arena into our list, and if you pass no arena, it uses malloc. But if you pass it in arena, it uses the arena to allocate. This would be great, but I don't want to do this now. Just I had the idea just now. Okay, so can we test this a little bit? Do I want to automatically test this? I think I don't want to test it. Let's just ignore testing right now. So now we have basic automatons. Token. So what do I want to do now? So let's peek to our to-do list basically. So we did this already, and we did this today. So basically we now have for each token we have one finite automaton, but using epsilon transitions. So it is not deterministic, but it doesn't matter right now. So this was the first step. So the second step, let's see. So let's commit this before I do anything else. Okay. Let's commit the change to charset as a separate thing. Reduce charset empty and non-empty. No explanation required. Now in this one, well, doesn't really matter. I'm not going to, well, just an idea. So yeah, so I'm just going to change just going to commit this all together. Now I think so. This one can be committed separately. Print epsilon only args little nicer, little bit more nice. Well, so in this one, change should be fine altogether. I will just commit this all together. So this one construct NFAs for regex tokens. So now, what do we have to do next? We have to now, so I think I was not really perfectly specific here. Combine NFRs into single NFR. FA, of course. So now we have a non-deterministic finite automaton for each token. And now we have to combine those to a single NFA. So, and the way we are going to do this, I think we're just going to combine it into a big automaton. But let's think ahead quite a little bit. So let's say we have a big automaton, a really big automaton, which basically knows how to detect a lot of different kinds of tokens. So for example, we have a token if, we have a token, let's say A to Z plus. So this is the automaton which recognizes this pattern. Oh, and I saw another problem. So this token could potentially be the prefix of this. How do I want to do this? So for example, if fx, for example, if x is this, does this pass as a keyword if? So does this, let's say, let's give them numbers to talk about what I mean. So should this use the string, the token string 0, 1, since if is a single keyword followed by an x, which could be an identifier, or do we want to always pass fx if x using 1? So basically, do we want to support this? So I think I would like to do this. Can you somehow disable this? So what do I have to do then? I think the ordering of the tokens matters if you would like to handle this case. Since, well, this pattern would also be completely matched by this token, but I would like to have this as a separate token. So I would like to handle this case, I think. I don't want to return if as an identifier. So I want to parse this. But then, of course, this one is more specific than this one. So I think I have to, so the ordering matters of my tokens. This is what I learned. Well, since if I switch those in my scanner generator, this would swallow this. So I think ordering matters. So, but ordering is fine. I remember the tokens in the ordering the user gave it. So this no problem. But then but now let's think of the situation. We have a combined regular expression, a combined automaton basically does the same. So then I think I can't combine the accepting states. Yeah, so I can't do this. Since now, if this state accepts, we can't differentiate if this token was detected or this token. I think those have to stay separate. Let's just say, okay, in this case, well, this was a beautiful circle. So in this case, we accept with the token, let's keep the numbers, we accept with 0. So this is a 6. Perfect. Thank you, my computer mouse. They accept AC. This horrible mess should be an AC. We accept with token 0. So I'm calling it token 0 in this case. And in this case, well, I think I have to buy a graphic tablet. But for now, I don't have it. So in this case, we accept, and we detect the token 1. So this makes sense. And the token, well, where are we here? So, and I think the problem was describing here actually was fixed itself since I fixed the formatting, the perfect forwarding in our logger. So I think this problem fixed itself. So let's just try it. So format. So let's not worry about this. Okay, sure. So now we have an automaton for each state. Do I have to build a single and play out of those? So let's this. So let's refactor this a little bit. So let's remember our automaton here, and not as a const reference. No, not really what I expected. But so this one is. So I'm adding this later. Then moving it aside. But then I can't refer to NFAs one until I add it. So and now suggests to use a range-based for loop. Yeah, but I think I need the integer. So because the index also is could be used as a token ID. So I think I don't want to. I want to always have the integer here. So I think. So how do I proceed? I have to combine everything with a single automaton. Okay, I think I have to combine it. Every single automaton, but I have to keep the original end states and each automaton. So let's say the following. Let's also attach the automaton's index, the token index here. So let's just what do I want to create in type alias for that? So I'm trying to think a little bit ahead here, but I think I will not overcomplicate the things. I'm just going to hack it and change it if applicable. I think this will be a little bit easier than just. So, but now I could also return the automaton from here, I think. I think this would be a little bit cleaner structure than. So let's just, so I'm passing in the arena. Let's refactor this a bit. Let's say automaton. So let's say this doesn't return a boolean, but this returns an either of a error, so a string view for now, a string view, or an automaton. And then we don't pass in a mutable reference. So, and then now what do we do? I'm just going to create an automaton here. So we got to pass it the arena, and in this case, we're just going to we return a successful either, so a right. This case, same thing. Automaton case, we're just Let's just deal with the happy case first. We return our what I'm doing is remove automaton. Automaton. So the happy case. So this case is a crash. So I can just return something stupid like result left, for example, reachable. Since this case is all reachable and always crashes, this is just a dummy return. I can also return a string then, a string view, a null string view. And in this case, what does this return? It already returns an error. So I think I can just, but what does it really return? Does it return an error? It returns a string view. So this to-do we are working on right now, we don't need to print. We're just going to return a result failed either, so a left. We're actually moving the error case release left. So we're just moving the nested error into a new result returning. So currently we are returning string views, but this won't be forever. So this warning, currently string view is trivially copyable. So, but I think we will change this in the future. So I think I'm just eating this warning. So, and in this case, we of course this case, we change this code to, so this call stays, but we don't pass the automaton in, we get it back. So then, if we have an error, we just propagate it. So I think I can repeat this horribleness. So in this case, we just return. In the other case, we have an automaton. So we just, well, I just noticed that I could write automaton because auto is a keyword. But I think I don't like this pun. So release. So we release the automaton and we move it into our local variable. So now this code compiles and then we remember our automaton here and we print it in the meantime. I think this should be a great little refactoring. Let's see if it works. Don't know if automaton is movable. Looks like it works, so let's keep it. So now let's remember which token. So what do we get here? We get a token. So let's remember the token. So the token list should be stable, but I would like to do it a little bit differently. So let's do the following. Let's construct the result type here. So I think also the arena should be part of our grammar, since I want my instances to keep alive till this instance dies. So let's restructure this. So what is a class grammar? It just has a public method compile. Perfect. So we are in this class. I see. So we're in the static factory method. I can find. I would like to do the following. So our specification just remembers the tokens. Sure thing. Now let's also keep those, our resulting grammar. Token spec. Where is class token spec defined? It is inside of our specification. I don't think I need to do this, what I'm trying to do here. So, so let's roll back. So I haven't made up my mind what to do next. Maybe let's just commit. So I don't want to keep this change, but I want to keep this change. So I refactored a little bit and I propagated error. So propagate errors from auxiliary functions to grammar compile. So now that I have these single NFAs, I have to really construct a combined one. So let's see. We have to remember which token this accepts. And how do I do this? Do I give it a integer or a pointer? I'm just giving it an token ID. So each single automaton maybe I can skip this step. So what do I need to do next? So let's just do it. So basically, I now have to eliminate epsilon transitions. Yeah, need to eliminate epsilon. And construct a deterministic finite automaton. Our current automatons, they do have epsilon transitions. Of course, in our scanner generator that we are creating right now, we don't want them. So, for example, your input file of your language, you always have one character after another without epsilons, of course. So, for example, an example program could be 3 + 4 maybe in parentheses, and then space times 5, like this, for example. So, and each character you consume, you have to decide which transition you take. So, so ideally, we would like to create a transition table, which the computer can execute basically. We don't have to simulate those kinds of, so we don't have to simulate epsilon transitions. So I think we will do the following. So how do you do this? So let's start a new document. If you want to combine them, so for example, you have to, so I think we have to do the following thing. How do I start? Okay, cool. So let's consider we have the following automaton. So non-deterministic automaton. We have a epsilon transition where we reach this state. So let's give them numbers to differentiate them. And for example, you have accept the character A here, 3, and then another epsilon where we reach the accepting state. So like this, for example. So this is a non-deterministic automaton since it contains epsilons and each label. So and the labels are distinct. So a deterministic finite automaton, each label is distinct. So for example, this would be also a reason why this is not a DFA. So this is an NFA since it contains epsilon transitions and the transitions are not distinct. So each state, you can reach different states with the same symbol starting from, you can reach different states with the same character starting from 2. So in this non-deterministic finite automaton is also not deterministic since it contains epsilon transitions. So I think I found the correct words to describe it. So, and of course, this NFA can be represented by a very simple DFA, which is just a single state, and then we transition to the next state with an A without the epsilon. So in this case, it's really easy. And how do we get from here to here? So basically, let me redraw this with a little bit. So basically, we simulate our non-deterministic automaton, construct a one DFA from one NFA, and we do this by looking at the states which are reachable from one state. So this NFA can be represented by the DFA, where we basically merge states 1 and 2, and we merge states 3 and 4. And there's an algorithm which does this, which we're going to implement now. So, but I think I would like to do the following first. So, of course, we are creating a new method. So maybe let's rename create automaton. What is this one called? Okay, let's rename this to NFA. Now those are just helper. Let's call this one create NFA. Yeah, create NFA. So, and I'm thinking I'm doing a similar thing, but I'm going to create DFA here, a DFA. I'm not really sure. I think this is always possible. So if we have a correct NFA, which we do by construction, then creating DFAs won't fail. And if it does, we can always fix it. So, and here we don't pass in the token, but we pass in the NFA. So NFA automaton NFA. Of course, I think we don't want to return NFA. So let's introduce another class which holds the DFA. And it should look a lot like this class, but Epsilon, basically we don't have Epsilon transitions. I think I can just copy the whole thing. Or do I want to reuse the data structure and just have the implicit knowledge that my automatons are deterministic? Let's do it for now. I don't feel like creating a new data structure. So let's just reuse this one. So I think we can't do this. How do we do this? So I have to simulate multiple automatons at once. So let's create. I don't know how to do this. Where do we start? But I think I pass in all NFAs at once. Okay, let's do this. Pass all NFAs at once, create a single DFR out of it. So now, of course, it's not implemented right now, so we're just returning a dummy value. So let's sketch something out. So I think I have to apologize myself. I'm not really really concentrated today since a little bit I have a little cold, but I think I still think I'm able to do this. So to create a DFR, what do we have to do? We have to combine states. So we need a way to reference a state of an automaton. So we have an NFA state. That's for easy access, let's remember the automaton. So we can always search, but so this, oh sorry, I have to also remember the state. So this is a state of an automaton, of an NFA, where we also reference automaton. So of course we could also search this state inside of our automatons. I think I'm doing it like this. So basically, so in a state of a DFA is a set of, so I don't have a set data structure yet. So let's sketch it out using lists. So let's for now say using set is list. And also template type name. I think I have to sketch out a hacky set implementation for this. So a set of NFA states is a DFR state. So those are the NFA states. And this one also references, let's name this field to NFA to be more clear. One is a DFA. So I think a DFR state is just a set of NFA states. And then, of course, we construct a DFA state, and then we simulate all of those automatons in parallel and see which transition takes us to which state. And we just record this as a new DFR state. And during simulation, we build the new automaton. Let's try this. So let's hack a little Z together. So what does a Z need? Contains, add, basically. Can I just use it? Do I have list contains? Yeah, but the ordering doesn't matter in a set. Yeah. So I'm not really in the mood of implementing a set, so I'm just hacking something. So a set is a class which is templatized over T. And for now, I just implement it as a list of T. Got to include for list. Of course, so this should be it. So, and of course I have following methods. I also have a, so let's implement, So I don't have a contains method. Let's do a contains method on our list. So bool contains let's put it next to add. And of course, for lists, we iterate through our list. If lm is value and true, else return false. So really basic contains method. So and set just does the following thing. So basically also introduce a contains method. So let's actually make our lives a little bit easier, a little bit more easy, and add our set to the make. And our contains method just forwards to our list. Easy. So we're just linearly searching, and our add method now does the following. So this is where the hack begins. To add a value t, value, we're just, so I'm doing this out of line, I think. So value and so to add a element to a set, we check if it already contains this element. And if we already contain it, we just don't do anything else. We just add it to the underlying list. So really hacky for now. And of course the move thing. Same thing here. So I think this should be a working set. Of course we can't iterate over our set. But we can iterate over our list. Hello? Okay. Just steal the iterators for now and just delegate to the lists iterators. So just I will just delegate to in end. So and this should be fine since the iterators are read-only basically. So just delegating to the list constructors, so I don't have to reinvent everything. So then I have a set class, a perfect low set class, but you can always change the implementation later. And we are going to do that, but not yet. So now this should actually compile. I know what I missed. So I need to use this, export the symbol into the global namespace. So this should work now. let's create a result automaton. And let's create its first state. So what do I have to do now? I now have to map so now I have to do some bookkeeping, but I'm not sure how I do this. DFA. I think I have to keep track of the different states. So I think I have to cut here. And play with my cat. Hear him? I think it can't hear this. So maybe let's see what we need to do next. So I first of all create a new state. I have to attach information to our state. So let's sketch it out. So basically we create a new state. This is our start state. So but we have this is our DFA start state. So then I'm just configuring it as a start state. Fine. So and then I have to create the corresponding set. How do I do this? So I go through Nfa state. I think I can just put it here. So those are the NFA states. I also keep track of the DFA state. And of course those are pointers. Are they? No, they are not pointers. So this is the DFR state. So and to create this instance, I have to find all NFA states. How do I do this? So I don't need this. So basically I have to create such a thing. So this is the DFA start. Let's define this as structs for now. So the DFI start. We assign the let's drop the horrible prefix. So the DFA state is this one. So Nfa state. What do I want to do? The Nfa state is it is an NFA state. So I'm not really sure how I want to do this, but something like this. Or like this. Our DFA state but this is a DFA state, so maybe I have to introduce different types. So our DFA state is a new state. And then I also can configure it as a start state. So fine, this should be it. So and now I have to basically go through all of the corresponding NFA states. Construct this list. So let's construct this manually. So let's just go through all NFAs. And create an NFA state for each of this. So this is an NFA state. Right? We remember the NFA and the start state. So like this. So let's create a helper method for this. NFA state, and we pass it a NFA automaton, of course. Start. We iterate through all states for states. So I'm currently programming over my cat. So, but he seems to enjoy it. So yeah. So basically, if our current state is a start state, we're just going to return. I think we're going to remember it. So doing the following state result. So then, if the current state we are looking at, we assert that result is null pointer, we'll just crash for now. Multiple. So basically, we see a start state, but we already seen one previously. Then we crash for now, and else we remember the result state, and we continue. At the end, we either crashed or return a start state of the automaton. So now we have a single NFA state. So this is a start state. So let's collect them. Collect them in the current state. So DFA, we add it to our list of NFA states. So, and I think I don't have a equals method for NFA state defined. Fine, this will be easy, I think. Just implementing the operator equal. I think this should be it. Okay, so now we have the first state. But of course, so now we have a DFR state containing all NFR states. So for example, we have a picture always helps to visualize. So let's say our NFA looks like this. We have an state 1. Let's just build something. For example, we have something like this. Oh, no. Let's say we have those two DFAs and NFAs, sorry. And here, basically, let's just keep it simple. Let's say those are accepting. So now a DFR state, our DFR state which we currently constructed looks like this. We have a new state which contains all start states of the NFA. So I'm now writing basically a set of states using curly braces. Currently our start state looks like this. Oh no, sorry, no 3, not 3, not 1 and 2. So we have the start states of each NFA. But this state can spuriously transition to this state using the Epsilon transition. So we have to include every states which are usable by Epsilon as well. So, and now we are going to do this. So what we have to do now. So let's implement a method which does this. So this method I'm going to call and epsilon. And we are passing a DFA state. I think a DFA state is enough since we know so we have I think a DFA state is enough. So well, we haven't defined it yet. And then we are basically going to say expand epsilon Nfa state. This is the plan, but I don't know if I should also pass in the automatons, but the knowledge is already wired. So in each Nfa state of our DFR state, so I have to also append it. So I forgot the most important thing. So our NFA states, oh, well, we already do this. Well, I didn't see this. So let's move it. Oh, we want to stay here. Oh, sorry. Hi. So if I would like to expand the epsilon, then I have to go through all of our states which we already contain. So for each NFA state in our states, so basically we're going through those. Now we have our automaton here. So we're just, this is this automaton, and now we have to add all on the NFA state which is reachable from the state. So reachable by. Let's model this. I would like to say something like bool for each reachable I give it an automaton, so an NFA automaton. And I give it a state, so a NFA state. Then I'm going to give it a callback, so a type name callback, and I'm accepting this argument. Just going to iterate through all states. I iterate through all states, and if through all arcs. I'm iterating through all arcs, and my origin, the same as my state, then I'm going to call the callback with the reachable state. But the arc carries information about the position thing. So the callback accepts the arc. So then I can say for each reachable, I pass in my NFA and my NFA state of my NFA state. Well, no, that can't be right. Sure. Yes, it is right. So now I pass in the arc. I get the arc. So sigil NFA arc. Now I check. Let's just say So I think by construction we only set either. So let's see. Let's assert. Let's assert that we either have a non-empty char set or a epsilon transition. I think this is done by construction, but I'm not quite sure. So let's just assert it, since I'm abusing this fact right now. So if we are an epsilon transition, then, so if we don't are an epsilon transition, then we'll just skip this arc. We only care about reachable states. So, and in this case, we are an transition, so we're just going to modify. Oh, we are just iterating through them. So I think we're just going to do a, we are doing a new set, calling this reachable by epsilon, but this should be clear here. So then I'm just going to append all reachable states. So let's construct a new state and steal them some code here. So, and of course I don't have to set the start state here, but I have to remember the reachable. So maybe we don't want to, let's not remember them as const references. I don't really care. I do want to work them. Do want to use them. So then we just std move our NFA state to the set of reachable states. And at the end, we are expanding our, we have to do this more often. So I think we have to repeat this while true. So we always try to expand, and if reachable, so we first swoop we collect each reachable state, then we say for each reachable, for each state from the reachable states, if so I think I can already see where this is going. So we're repeating while we were modified. Here we reset the modified flag. And basically we're trying to insert our element into the state set. So if state NFA States contains Ln, if it is not yet, our element which is reachable from our current state is not already in the set of NFA states, then we add it. And And we remember that we modified. And we repeat this for all cases. And then we do another round. So basically, we are modifying this set and following all iterations, all epsilons. So now, in the first swoop, we only collect 1 and 2. So then we do one iteration of expand epsilon and follow 3. But 3, of course, could potentially, not in this example, but could, for example, reach 2 different states, which are also reachable by epsilon, for example. So each iteration expands our graph by 1 step. So now, I do call this. All calls are unreachable. No, I don't think so. Because I'm because I don't call create DFA. So let's call it create DFA with our arena, our NFAs. So let's see what happens. I think so. Let's simplify our example. So what do I expect? So let's remove our first token. So let's simplify, see if code actually works. So let's do plus and star for now. Well, didn't want to do this. So let's do this. I didn't try to build before this. I changed this. No, not const anymore. I forgot to change the auxiliary function. So what happens if we run this? Cool. We have multiple start states. Didn't expect this. So let's follow the execution. So let's see what happens. So we come here, so we get here. This is good. We create a start state, which we configure as a start state. Perfect. Then we iterate through all NFAs. Let's follow this call. So this state is a start state. Result should be not null. So it is null. It should be null. I see. I messed up the assert. We should not have seen a valid. So we assert that this is not null, since we expect that we did not see a start state before. So just messed up the assert, I think. So let's see. So now this worked. We have a NFA state. Sure, this is the NFA where the state is from. We have a state. This is the start state. Cool. We will remember it. So now we should have a DFA with 2 NFA states. This is the case. Then we expand epsilon and follow epsilon transitions. We're iterating through all reachable states. No state is reachable, so we should break. We break. So this one should wait. I think it didn't work. So NFA states. We have two NFA states. Yeah, sure. Now this fails, but why doesn't it work? So build these start states. Then expand epsilon. Why doesn't it work? Oh, we're using this automaton, this state. We're trying to. Do we come here? Try again. Do come here. So then we get an arc, so are reachable. From our start state, we reach this state, but this one is accepting. Don't allow an epsilon transition, but here is some character. Okay, sure. So this one, not an epsilon transition. So we return, fine. Come here again. I think our example is just stupid. So let's just say, well, this is literal. So let's say AB a different example, for example. So let's say something like this. Now let's see what happens. So we create two NFAs, two NFA states. So our TFA state now contains two NFA states, which would be correct. Let's see what our method does, function does. So check which state is reachable. So flip it. So do we have, can we reach some states? Yeah, we reached 4 states. We try to add them. We reset our flag, try to add it, and we reset our modified flag. So now we repeat one step. So are there reachable states? There are. So okay, this was too fast. We added them all. So now we have 6 states. Sure. Let's draw out the okay. Okay, sure. So let's draw them. I think this should be a lot clearer. So we have two automatons. Let's draw them next to each other. So we start at state 0, the first one. Yeah. Okay, sure. So then if a 0, sorry, an epsilon, sorry, to transition in state 2 spuriously, but also in 1 also spuriously, but 1 is accepting. So 1, no outgoing edges there, and from 2, using A to 3, and from 3 using epsilon to 1. So this is one of our automatons. The second one is similar, but not the same. So we start in state 0. So those states are called the same. Going to be a little bit harder to reason about them, but it should be fine. I'm just drawing the automaton which is given by this printout from 1, 0, also by epsilon 2, epsilon 1. So they look almost the same. Sure. By epsilon. Sure. So let's do this by hand. So let's construct the start state. So in states of this automaton, I'm prefixing with 0 colon. So for example, 0 colon 0 is this state. 0 colon and 1 colon 0 is this state. So to keep them separate. So now let's construct the start state of the combined DFA. So we start both start states in the first automaton. So 0, 0 and 1, 0 basically. So, and in the first iteration of our expand epsilon, we should see 0, 2 and 0, 1. 0, 1. So those two states, they are reachable by epsilon. And then no further states are reachable from those. So this should be this automaton, and then let's just see what the first iteration does. So then you reach also state 2 and 1, but in the second automaton using the start state. So from this state, you transition via epsilon, you reach 2 and 1. So 1, 1. So let's see. So this was the first iteration. Then we look at each state again. So those states are actually handled. So I'm not going. So let's see what happens. So we go through each of those states again. So 0, 0. We also handled the reachable states, so we don't add them again. And also from this, we handled them again. Then from 0, 2, so from this state, there's no state reachable. from 0, 1, also no state. So those are also handled. So let's tick them off. So from this state, so let's tick all of them off basically. And from this state, we have no state reachable by epsilon transition. So tick this off. From this state, we only have this state again, which we already added to our set, so we won't add it again. So handled. So this we should get a set with 6 states. I think I saw this earlier. So let's call this method again. Let's run and let's see what happens. So we get a set back with 6 states. So it seems to work, but it's a little bit harder to print. So maybe I should just print them in a similar fashion using the colon notation. So what if I don't store the NFA, but also the NFA, the token ID, so to speak. So why do I construct this? Okay, but I think this should be it. So now we have to count the first state in our DFA. Perfect. But how do we proceed? I think now we do the same, but with each possible character. Possible character. I think I need some abstraction that I don't have to those primitive operations. So for example, this bookkeeping will get really hard later. But I think let's maybe cut here. I'm getting really tired already recording 3 hours. So I think we did some great progress. We added a really basic set. Just defines a set-like API, but delegates all calls to lists. So really inefficient, but don't really care. Then we added creation of non-deterministic finite automatons from regular expressions. This went really smooth. Really surprised that it worked so well. But now we are getting to the hard part of bookkeeping. And we discovered we're basically in the middle of creating a deterministic finite automaton from non-deterministic ones. We do this by merging states which are reachable under the same character. So basically, the idea, going to spoil, I think. Well, first of all, we merge all states which are reachable from the start state. Then we simulate the combined automaton to transition a single character, for example, an A. And then this state we also epsilon expand, and then we get a new state. And if we did not see this new state, then we create a new DFA state using this. I think I'm going to change the code a little bit. The next time, but I think the basic concept, the basic idea is fine, but I think I don't have to, it will be easier to reason about if we do this a little bit different, and then also can always refactor it later and make it more efficient. For example, I hated that I have to allocate this set every time, but let's just make it work and we can always optimize it later. So the plan is next time to continue creating our DFA from the NFAs. I hope to see you again. Have a great day. Bye.